Thank you, everyone, for coming to this Earth on AWS session. We're going to have NASA and Element 84 up here in a few moments to talk to you more about NASA's missions and goals and some of the challenges that they're facing and how they're technically dealing with that. But I'm going to start briefly by talking about the Open Data program on AWS. And I'm super excited to have the honor of being up here alongside NASA, who has made amazing contributions to the open geospatial data throughout its history, and Element 84, who is an integral part of continuing this into the future. So one of the questions that I get a lot is, why does AWS care about open data? Quite simply, we care about it because our customers care about it. So many of our public sector customers use AWS to make their data available to global communities of researchers, entrepreneurs, and students. And then on the flip side, we have a lot of our commercial customers who rely on that data. So they rely on that data being a base layer that they can work from scalably in the cloud, just like they rely on our infrastructure. When we think about open data, what we see is that a lot of people end up doing the same repetitive tasks over and over and over again, right? So anecdotally, if you've worked with data, you know that's probably about 80% of the work until you get to the point that you can actually do something with that data and start getting answers. So we see that as undifferentiated heavy lifting. So if that's something that we can remove from our customers having to do, then we can add value for them. So what's a practical example of this? So this is a graph by Drew Bollinger from Development Seed. And what Drew was doing was accessing Landsat 8 data. He was accessing it in a traditional mechanism via machine-machine or similar like FTP. But then he switched to using the Landsat 8 data, which is satellite imagery data that's available on AWS. When we made this data available in AWS, we actually unarchived the data. So it's no longer packed together. It's unarchived, and you can access the bands individually, right? Because it's not often, if you're familiar with the satellite data, it's not always the case that you want to get access to all the bands at once. You might just want some of the data from that scene. And so the difference here is via the traditional mechanisms, the access time was on the order of minutes. And when he was using the data on AWS, the access time was on the order of seconds. So this graph corresponds to about 100,000 requests for the imagery. And that means it's about 200 days of Drew's life that he does not have to wait to get imagery, and he can start working on it. So that's the sort of undifferentiated heavy lifting that we're looking to remove from customers there. And in this case, it's just as simple as unarchiving the data and making it available in that format. So a couple other things that we think about is that opening up the data is just the beginning. It's not the end. Users need to understand what the data is and how to use it. And then they also need to have tools to be able to process and analyze the data. So even if there is some way that I could give you all petabytes of data, and even if there is some way that you could store petabytes of data locally, it's probably not the case that you have the processing power to work with those petabytes of data locally, right? So when you bring your algorithms to the cloud and work with the data in the cloud, you have access to any sort of compute resources that you want. So it fundamentally changes it. And so this has a very democratizing effect on the access to the data and who can work with the data. It's no longer the case that you need to be sitting on a supercompute facility or just even very high-end hardware locally to be able to work with the data. So it has anyone can analyze any volume of data when it's made available in the cloud. So the Open Data team, we sit on top of the public datasets program, which is about 6 petabytes of data. We'll talk more about Earth observation data here later. So that's one piece of it. We also have a lot of life sciences and genomics data. And we also have a lot of data that's appropriate for machine learning. And if you just search for AWS public datasets, you'll find a listing of all those datasets out there. So for the Earth observation, we started this about 1.5 years ago. It's the Earth on AWS initiative that's also in the name of this session. And so basically, this is a home for geospatial data in AWS. So it has links to datasets that might be of interest. There's climate models, aerial imagery, elevation models, OpenStreetMap data is up there, satellite imagery. So there's a whole bunch of different types of data. But then it also has our customers talking about how they're using those data, right? And how they're using AWS for that data so that they can help you all learn how to get started with AWS and geospatial data more quickly. And so I'm going to get off the stage here in a second and bring Kevin up. But I just want to tell you that if any of this, what I just said, piqued your interest, or if you hear anything that Kevin or Dan talk about, and you're looking to do geospatial work on AWS, we have an open call for proposals for groups looking to do geospatial work on AWS. So please go to the link here or find me afterwards. and we can help make sure that if you're trying to prototype something or see how your current workflow would work in AWS, we don't need the infrastructure cost to be a barrier initially. So we can help out with that. So with that, I will hand it over to Kevin. Thank you.
All right, thank you very much, Joe. All right, so my name is Kevin Murphy, and I'm the program executive for Earth Science Data Systems at NASA headquarters in Washington, D.C. Again, I'd like to thank Joe for setting up this session, thank Amazon for hosting a reInvent every year. It's a great audience we have here, and I look forward to kind of describing some of the activities that we do at NASA. This presentation really covers how and why the Earth Science Data System was originally conceived and our plans for the evolution of this in the future. The Earth Science Data System program really fits into a whole host of capabilities that NASA has to develop satellites, launch satellites, run aircraft campaigns, and analyze data about the Earth, right? And the way that the Earth Science Data System program complements all of these kind of research and engineering development activities is by actively managing NASA's Earth science data as a national asset, right? These are data that taxpayers have funded and that should be available to them in a really wide way. And we develop capabilities that are optimized to support rigorous science investigations, right? So that's a little bit different than some things because we'd have to make sure that we know where the data comes from. We need to know the provenance. We need to know what was done to the data. So if we do temperature records or sea surface temperature records, those types of things, that we have confidence that they haven't been changed. We process, and probably more importantly, reprocess the instrument data from these multiple instruments to create high-quality, long-term Earth science data records, right? So if you're trying to look at ozone over 30 or 40-year period of time, right, satellites don't last that long. So you need to be able to process and reprocess things so that, as satellites degrade or as the capabilities improve, you can have a consistent long-term record. And we're probably the single largest repository of multivariate heterogeneous Earth science data in the world, right? So we've got around 24-ish petabytes of information. Now this data doesn't just support scientists, right? We also support application users that do like wildfire management, monitoring sea ice for navigation, supporting like fisheries management, those types of things. Earth observation has always been, a lot of people ask, like, why is NASA doing this, right? But Earth observation has always been part of the NASA Charter since 1958 when NASA was originally conceived. And we provide these long-term continuous observations to do these climate types of things. One of the first examples of Earth observations were weather satellites Noaa built in the early 1960s. Now, for the first 25 years of kind of NASA's existence, we really didn't understand the value of free and open data. But about in 1994, it was determined that to extract the full value of the products that we have and the future products that we will acquire, having a free and open data policy was really, really necessary. Now, we do have a couple caveats on that. Like, we need to make sure the data are calibrated and make sure the instrument's operating properly before we get it out so people know what's going on. Now, we're going to spend a lot of time today talking about something called EOSDIS. And we use a lot of acronyms at NASA, and so afterwards, if I say too many acronyms, come up and beat me up. I'll try not to do that. Anyhow, EOSDIS is the Earth Observing System Data Information System. It's basically the capability that was built to adhere to this free and open data policy in 1994. It was really built with 1990s kind of technology, and it's worked very well. Now, if you see this middle box here, what EOSDIS does is really process, archive, transform, and distribute the products to any types of users. We also work quite a bit with missions as they're on development, aircraft campaigns, field measurements as well to get the data in formats that we need, work with satellite ground stations, those type of things. Now, how do we do it? Well, we got a lot of people, and we have them geographically distributed throughout the United States. And the way that we do it is this. You imagine satellites transmit data to the ground, right? Then we have these things called science investigator-led processing facilities, which process those instrument data into higher level products, right? So we call them like level 0 comes from the satellite, level 1 is a basic type of data, level 4 is like model output. And we process it through all that chain of things. The data then go to these things called Distributed Active Archive Centers, or DACs, which are based on science disciplines, and they do the public distribution, right? They have the responsibility for the long-term archive, and they develop specialized end-user tools and services for the science communities that they support. Now you can imagine, a physical oceanographer has a whole different set of tools that he uses or she uses than an atmospheric scientist who may use a whole different set of measurement types and techniques and even languages. And that's what these DACs do, is that they help translate the information that we have into these communities. And they also play a critical role in helping us evolve the systems over time and those capabilities. We got about 3 million users per year that use these things. We ingest about 4 to 5 petabytes right now per year into this system, and we distribute around 24 petabytes per year, right? So we really are kind of an ingest and distribution system with some search and discovery in there. But we need to link these pieces together, right? You can't go to 12 different spots and go and find the data that you may need to do integrated Earth system science, right? Lakes and rivers and oceans are all connected, and they are slightly different in terms of how we carve up the data. So we need ways for people to access the entire archive, and actually archives outside of NASA, to accomplish their science goals. And the way that we do this is that we have some things called EOSDIS common services. And they provide common discovery, visualization tools, and services spanning all our DACs and SIPs to improve the discoverability and accessibility and usability of our products. These are all based, well, increasingly based on open APIs. Maybe we don't have all open APIs at this point. But this allows developers, maybe in this community, to mix and match those services to develop clients that they can use to satisfy their own communities. So like a really good example of this would be, PBS has a clouds lab, and they invoke some of our services to help kids understand components about Earth science, right? And they don't have to use our clients, they can just go use the APIs. We also interface with other international organizations and governments, right? We have a lot of partnerships with CEOS, which is a Committee on Earth Observing Satellites, and that's kind of all the space-faring nations that look at the Earth. And we interoperate with their catalogs using standard-based metadata on concepts that we develop in conjunction with them. And we work with the European Union and many others. And I'm going to probably show you some of this stuff in a few minutes, but basically, our open service APIs and our open service clients are all open source as well, right? So if you go onto GitHub and look for NASA data, you can see many of these things. And one of the things that we have really changed in the past 2 years is that everything we develop, not only for these core services, but all of our next generation, like ingest and archive systems and data management and analytics systems, will also be open sourced. So this community is welcome to take a look at this. Now, a core component of EOSDIS is the ability to search quickly across close to 400 million objects, right? In space, time, by science variable, by quality, right? And it took a lot of effort by actually some of the people in this room to make this possible, but we've been able to make our search repository sub-second search results, right? So you can put a bounding box somewhere, you can look for over 35 years or so of data, and it will match that stuff for you, right? Very quickly. And that's a core thing that we need to do too, right? We need to make the things that we develop interactive and usable by people, right? And speed in that user experience component is highly important to us. Now this is really complicated too, because you may recall that we're always processing data and we're always reprocessing data, so the actual information in there changes. I think we updated 3 or 4 million granules a day, right? That get changed at least. Anyhow. Now also, we were able to use AWS to help and even improve what we had done. So I think we started the CMR project, 5 years ago or so, built it out onto an on-premise solution that really achieved 90% hit rates within sub-second search across all 400 million or so granules that we have. But by moving it to AWS, we were able to improve that and kind of reduce the sustained engineering costs that we could plow back into more capable technologies. Now, there are two two main ways to look at our entire data archives, right? One is really a data-centric user approach, right? So if you go to something called earthdata.nasa.gov, that's our primary kind of portal into all of our data products and our DACs. And it has something called Earth Data Search. So if you really know what you're looking for, right? If you know that I'm looking for, an atmospheric temperature at this altitude, you can put that type of stuff in there, right? Or it's millibars, right? It's not altitude. But if you're more of an imagery-centric type of user, we have a thing called Worldview, which shouldn't be confused with the satellite, but it's a web client that allows you to have access to our global imagery browse services, right? And that provides time series information for people to view. And what I'm going to try to do here is switch to the demo computer and show this. Okay, so let's see, what are you looking at, right? What you're looking at here is data from today. Okay, this is data taken by the MODIS instrument on the Terra satellite, which has about a 10:30 a.m. overpass time, right? So it does this every day. It looks at the entire world every day. We have a similar type of satellite with the same instrument that looks at the world at 1:30 p.m. every day, okay? And this is important because you need to have different types of viewing geometries, different types of illumination from the sun to look at different types of environmental phenomena. Typically, if you're looking like land type of information, you want to look in the morning because there are fewer clouds. And if you're looking for clouds, well, you want to look in the afternoon. We also work closely with Noaa. So we've been able to take the heritage instruments that you saw up there, which have been running for 17 or so years, and add data from this thing called SUMI-NPP VIIRS instrument, which was launched about 4 or 5 years ago. A sister instrument to this was launched called JPSS just a few weeks ago. So we plan on having these types of data available for many decades. Now just to show you kind of why it's important to be able to look across multiple domains and to understand how the environment is connected and how different components of the environment are connected. I'll give you a couple demonstrations here. First, we find that our scientists, and actually most users, want to be able to see things at full resolution, right? So we need to be having the capability to zoom in to full resolution, which is about 250 meters for this satellite. So a pixel is about 250 meters on the side. But they also want to see time, right? They want to see how the Earth changes. So we have a time slider at the bottom. It goes back, I think, almost a decade now. It's going to go back to about 1999 in the next couple of months, or maybe by the late spring. And you should be able to zoom out. You should be able to interact with these things pretty quickly. And that's pretty neat, right? We do a lot of polar work, so we need unique tools that represent the poles, right? Because you have different types of projections, different types of sampling capabilities at those locations, right? So we have some unique capabilities there. And probably the most interesting thing about this tool is that you can add layers on top of this. And those layers are our higher level products, right? So this is just a corrected reflectance image, right? It makes it kind of look like your eyes would see it from space. But we can see all sorts of different things in different spectrums of or different components of the electromagnetic spectrum, right? So if you click this Add Layers button, you have access to about 400 layers that we update almost daily that you can lay on top of here that look at things like, aerosol optical depth or how turbid the atmosphere is between you and the satellite sensor. We have really good background images where take out all the clouds, those types of things. We can look at ash plumes. We can look at fires, so on and so forth. And we can do that both by science discipline and hazards and disasters. So let's take a recent example to kind of show how this works. And we'll zoom into California over here. And we'll go back to early October, right before the fires in Santa Rosa. And we'll put some borders and types of things on there. And you can see, a couple days before the fire happens, the clouds are not there. It's on clear skies. You get some, cloud banks off into the Pacific, and they're moving around. And you get into October 9th, right? And you see these giant smoke plumes sprout up. We we also detect active fires. So we can overlay these active fire spots, or the pixels that have been designated as thermal anomalies, right, over top of these top of this background image. Zoom in and use these. And firefighters use these to understand where the fire is progressing, how environmental conditions are interacting with those fires. But not only that, and from the same instrument, and I'm not going to go into the like 30 or 40 instruments that we have in here, but you can start to look at the aerosol optical depth, or the smoke, right? And where does that smoke go once it's generated from these locations? If you use a time slider, you can go forward in time, and you can see that it kind of wraps around and starts going up into the northeast. Eventually, it gets all the way into like, Montana and Idaho, Wyoming, those types of areas. And when you see large fires like this, large disturbances, they can spread all over the world, right? And it's very important both for understanding how hurricanes form, right? How smog gets transported from China to the west coast of the United States. And you can do that visually with some of these tools. And not only do we, oops, that's what I get for using somebody else's computer. Not only can we do it during kind of the day, but we do it at night now. So maybe you've seen images of Puerto Rico or images of Florida after hurricanes and the loss of power, right? We generate these, what we call nighttime light constant stretch images every night or every day from satellites, right? So if you can zoom out, you can see they're available, right? And if we go to Puerto Rico here, we go to late August, you can kind of see this is Puerto Rico, and the intensity of light, right, is demonstrated by the brightness of these pixels. And so the brighter they are, the more light you see, and obviously, unless there's a fire, that's human-caused light. You can then kind of go, to right after the hurricane, and if you can get a cloud-free day, you can see a significant difference in this information, right? So not only can you look at how kind of the environment is interconnected, but you can look at how humans are impacting the environment with this. So that's it for that part. So I have a whole bunch of screenshots in here because we weren't sure if it's going to work, so I'm going to go real quick. Okay, so preparing for the future. Well, we've been doing this for a while, and we've been doing it consistently for a long time. And we have some pretty significant advantages on the horizon. Okay, so this kind of graphic, the lower half of it are things that are actually on orbit and taking data, right? And some of them have been up for a very long time. If we go actually this should be different. We have Cygnus launched as well. But the rest of these things are all taking data. ISAT-2 is going to launch next year. GRACE follow-on, which looks at gravity, looks at the reservoirs of water and aquifers, is launching. We have JPSS-2, Tempo, SWAT, NISAR, PACE, Landsat 9, a bunch of CubeSats, right? We have a bunch of things that are going on the International Space Station to take kind of unique measurements of the Earth. We have this other thing called the National Research Council's Decadal Survey, which prioritizes future measurements for us, right? So the things that you see here, we're bending metal or we're about to launch, right? And people, when they use our products, are expecting them to be more usable, which is actually kind of difficult. So we have a lot of challenges, right? And this kind of chart always scares me because I have to pay for it. But basically, the issue is that we're going to increase our ingest rates from about 4 petabytes a year to 50 petabytes a year in about 5 years with the things that we know that are going to launch, right? And we have issues with how we can pay for that, how we can access that, or how we can provide that in a free and open way, right? And that's kind of where a lot of our development activities have been going lately. And that's what Dan's going to talk about in a few minutes. But there's some key components to it because we need to have open data. We need to have open source software so people have trust in the results. And that applies to the whole stack of software, both in terms of our algorithms and science processing software, as well as any of the transformation types of software that we build. And so we are embracing a cloud native policy for these types of things. We want to bring people closer to the data, right? And I thought it'd be interesting. I had a rocket video in here. People usually like those, but they were like, no, you don't have enough time. So anyhow, I'll give you some NISAR quick facts here. So NISAR is basically, it's going to be a satellite that's a collaboration between NASA and the Indian Space Remote Sensing Organization. And it's going to be a SAR, a synthetic aperture radar imager, or not just imager, measuring capability. It has all weather capabilities, right? It can look through clouds. It can look day and night. It's an active sensor. And what it really allows us to do is look at small changes to the Earth movement, right? So you can look at things that pre and post earthquakes. You can come up with damage proxy maps, those types of things. You can look at flood maps, right, through clouds, those types of things. It's going to create around 38 petabytes of data a year. Okay. We have another one called the Surface Water and Ocean Topology Mission. There's a lot of text up here. But this is going to really change how our users interact with data, right? So people that are going to use these data are people that are traditionally using stream gauges, right? So they're out there measuring the height of water with a ruler, for instance. And now we got to figure out how they can use these high precision LiDAR measurements from space, right? And how do you do that? Well, there's a lot of education and there's a lot of processing behind that. Basically we need to better support our interdisciplinary earth science researchers. We need to understand how we can make our archives more interactive, right? We need to be able to afford it. We don't have a lot of money to do this. And we need to be able to work with others because we are not the only group that does Earth observations, right? So our model, obviously, and this is obvious while we're here, right, is to bring the data close to the compute, right? And to utilize as many services as we can to do that. And Dan's going to talk a lot about how we're trying to implement some of those capabilities. But what I'd like to leave you guys with is that, we have a whole bunch of open APIs. Like the imagery services that you saw on there, there's a WMTS or some sort of similar type of API available that can be used by anyone, right? We have open APIs into our CMR metadata repositories. We're increasingly having open APIs into our data itself. And we ask for everybody to help understand these products, develop products for themselves or their communities so that we can get this information into more people's hands. We do have, kind of like Amazon does, a way to give grants to people, and we have an access call out right now for people that want to do things with machine learning on this or develop, improve search results, those types of things. So if you're interested in that, you can come up and talk to me later. But I really appreciate the opportunity. And Dan, please come on up.
Thank you. All right, so I'm Dan Pallone. I get to talk about kind of how all this works under the covers and our transition into the cloud. I want to start out by saying I get the privilege of actually getting up here to talk about this, but what I'm going to talk about represents a lot of work from a lot of different groups. And so I want to make sure that they get the recognition they deserve. So kind of starting this off, as Kevin mentioned, EOS is really a set of interconnected systems, right? So we talk about the one he showed is Worldview and Earth Data Search. That's sitting on top of a high-performance imagery system called the Global Imagery Browse Service. This is Gibbs. You'll hear me mention that as we go forward. That's sitting on top of the Common Metadata Repository, the CMR, which provides search and indexing for all of that data, so you can discover the data that underlies the images that people are looking at. And then kind of making all of this possible is ingest and archive capabilities. And you're going to hear me refer to Cumulus. Cumulus represents kind of the cloud transition that we're doing for this. And then obviously backing all of this is kind of the infrastructure pieces around this: metrics, authentication, monitoring, and so on. So there's a lot of kind of moving parts, and then as Kevin mentioned, we expose a bunch of APIs which are consumed by third parties, and so there's pieces that we don't necessarily have control of or that we leverage, and so we have to kind of keep all that in mind as we make this transition, how it works, and you'll see that kind of come up in a couple places. But that's not even really the worst of it. That's not kind of the biggest piece. The biggest piece is that hockey stick graph Kevin showed. So just to kind of put a little fear, if we go back to NISAR that he had mentioned, it's 80 terabytes a day of data generation, kind of in a forward processing mode. When it's reprocessing, we're looking at 400 terabytes a day, which translates into 150 petabytes at 50 gigabits a second over several months. It's a phenomenal amount of data. The 300 gigabyte granules that are up there, so this data is carved up into smaller pieces so that people can access it. Those smaller pieces are up at 300 gigs. So really where all this puts us is that we have to change the paradigm. The traditional paradigm that we had used before, where this data is sitting at archive centers and people pull it down to work on it on their machines or pull it down and work on their facilities, it just isn't going to keep up with the scale of the data generation that we're starting to see and that we have to deal with. So we have to think about how do we do this differently. So I'm going to tell this story kind of from the context of worldview that Kevin had shown earlier. So again, this one's sitting on top of a system called Gibbs. Gibbs is the high-performance imagery distribution system. That was where we started. We took a look at that and said, all right, if we were to transition to the cloud, what does that look like? And what would it look like for Gibbs? What would we do? So at a high level, kind of just looking at a component breakdown, we took a look at Gibbs, and we kind of approached it from 3 different ways. First one was just, what if we forklift this? Just pick it up, drop it in there, do a cost model analysis on it. What does that look like? And the second one is, all right, let's take some of the low-hanging fruit, the obvious stuff. Let's swap out the database for RDS, things like that. But then we took a third pass, and we said, all right, what if we were to do this cloud native? If we were all in on AWS, what does this actually look like? So when you take a look at these services, what we did is we kind of went through them. So installation, we could swap out for CloudFormation. Inventory management, kind of the Gluster FS, the big file systems, and the RAIDs that we needed to deal with get swapped out for S3. Configuration management, deployment infrastructure, all that kind of stuff, again, CloudFormation. Subscription service, we can swap for SNS and SQS. Zookeeper, it's open source job management, can get replaced with DynamoDB and SQS. Authentication, we swap out for IAM. Management, I'll come back to that one. That one's going to turn into what we call the scheduler and the dispatcher. And significant event service becomes CloudWatch. So we take a pass at this, and if you step back, what we really end up with is something that looks like this. We collapse most of Gibbs into managed services. And what this lets us do then is really focus on where can we provide value. Let us work on, we're going to put our resources on the real unique business piece, the value add that we're doing, the data processing, data handling. This slide is a little bit dated. It's grown since here. But at the time when we first put this together, the 66 lines of code in the scheduler and the 106 lines of code in the dispatcher were really in the neighborhood of where it was. I mean, it was a tiny amount of kind of boilerplate code that we needed to deal with to kind of make this run. And it let us focus really down on that bottom row, which is the data processing and the conversion to imagery and building tile pyramids and things like that. All right. So this gets us excited. This is looking positive. We start looking at other systems. So we look at the CMR, the Common Metadata Repository that Kevin mentioned. And that one, we did a bunch of prototyping. We took a look at, OK, what would performance look like? Internally, the CMR is made up of a number of microservices. So there's kind of a lot of internal chatter between when a request hits, kind of do some internal processing, some searching, and then coming back out. So we did some prototyping in AWS to look at latencies. That was going to be a big deal for us, making latency requests across microservices, and what does that look like? And it came back great. It was going to be phenomenal. Sweet. OK, so we moved this whole thing up to the cloud. And then we start doing performance analysis. On the left-hand side is a graph of on-prem performance. And if I mark it here, that's 500 milliseconds. So Kevin mentioned sub-second search across the 400 million granules. The left-hand one, that's 500 millisecond response time. We were pretty consistent, occasional outliers, but generally it looked like that. On the right-hand graph, that is the AWS deployment. And if I mark 500 milliseconds, were there, right? And so if you look, there's actually a lot of white space underneath that 500 milliseconds. We were seeing performance times that were better than on-prem, but it was really noisy. And kind of our 98th, 99th percentile was significantly worse than it was on-prem. So this led to, overall, it was a much better scenario. We could move to more managed services, and we could manage deployment. We could scale things up. Like, that was all positive. But we had to then go back and kind of make changes to the system. Even though it was more of a forklift model, we still had to go back and kind of figure out how to smooth this stuff out, caching layers, things like that, to kind of smooth out this performance. So really, the big takeaway here is, once we, even with things that we forklift or nearly forklift, we still had to go back and kind of have architectural implications on those. All right, back to Gibbs. So we end up with something that looks like this for the Gibbs side. Scheduler, Elastic Container Service, kind of running in the background just to poke things periodically. Product configurations are all stored on S3. It pokes the Lambda function that goes out and looks for new data, sets up another S3 drop of here are some URLs we've got to go fetch and start moving this data in. That trigger ultimately triggers another set of Lambda functions, so we can kind of do this in parallel. We can do this across multiple data providers, across multiple SIPs that Kevin had mentioned earlier to pull this stuff in. Data gets pulled into S3, and then we can fire off longer running processes. So on the far right-hand side of that graph, that generating thumbnail, we move back into the container service because some of these things take longer than Lambda will let us do, and so we can kind of spin them up that way and do the processing. All right, so we're feeling pretty good. This whole prototype goes up, it looks good, it runs, we're pretty proud of ourselves, and then reInvent 2016 happens. And reInvent 2016, out comes step functions. So this kicks off this whole discussion of like, oh man, we just implemented step functions, we just did it ourselves, what do we do now? And it kicks off a whole nother round of discussions. And the discussions really revolve around where do we want to put, well, they settle on, where do we want to put our effort? If we make the transition to step functions, we can take advantage of that. We don't have to maintain kind of the queuing pieces that we needed to wire all these different Lambda functions and processes together. But it meant going back and revisiting some of the things we had just done this time last year. So if you look at this, this is October 17th to the 20th of this year. Right? So these are the announcements that came out in those 3 days. There have been, at the time I put this slide together, a little over 700 announcements from AWS related to services and features and enhancements and everything else. It's about 70 a month. It is so hard to keep up with this, and this is an ongoing issue, right? There's this constant kind of churn of the underlying infrastructure. They're phenomenal about not breaking things and not deprecating things and forcing transitions, but there's always something new and shiny out the other end. So we had to really think about it. We went back and we looked at our architecture and really decided that this was like so last year, and we needed something new. And so bear in mind, this was Q2, and reInvent 2016 was Q3, so we're like 2.5 months of happiness. So ultimately, we made the decision to do the swap. We pulled out kind of the underlying pieces we had put in, replaced it with step functions. If you notice in that middle bracket there, that workflow execution, that looks pretty similar to what was there before. A set of Lambda functions doing discovery and synchronization. We have ECS doing our long-running processing. Another Lambda function to send that data to the CMR. The data is being stored in S3, made available that way. And really what we've done is kind of replace some of the undifferentiated heavy lifting that Joe mentioned earlier, swap that out for step functions. Full transparency, this is still TBD. This is implemented, but there's growing pains inside of step functions too, and so there's just you're trading. But the thing that really pushed us over is that the scale at which AWS can deploy a service in terms of how many people can use step functions, how fast they can innovate on that, how fast they can build that out, anything that we were going to do in-house was going to be something we were going to have to build, maintain, and continue to push on. And it was resources that weren't going to kind of our unique business value that we were adding. So that was why that decision happened. So we get here. So putting that in context, it's kind of this piece. And I'll run through this diagram. It's going to show up in a couple times, so I'll run through this. So starting at the bottom is the SIPs, the science piece that Kevin mentioned. So data generation. Moving up the stack, you get into a Cumulus that I mentioned before. That's the step function piece that does ingest and archive. The cloudy thing there is the archive, and then sitting on top of that are a set of services. So I'm going to kind of walk through a couple pieces of this. So if you take a look at this in terms of mapping it over to AWS capabilities and managed services, it looks like this. So starting at the bottom, on the left hand, the HTTP, FTP, that's kind of your traditional science generation data. They're producing data on-prem, they're putting it in an FTP or HTTP location. We can fetch it and move it up the stack. The right-hand side of that one, though, at the very bottom, is basically a cloud-aware data provider. So this is someone who can do processing, data generation in AWS, putting the results in S3 and saves us a move. That is key to how we're going to handle things like Swat and NISAR, these massive data generation rates. We can scale those out in AWS, put the data in S3, and avoid moving 50 gigabits a second across kind of an on-prem network to get it into AWS. We can just produce it there. Sitting on top of that, we have Cumulus that I mentioned with the container service and Lambda and step functions and those pieces kind of tying that together. Sitting on top of that, ultimately, that's all feeding data into S3. Glacier, and then potentially an on-prem disaster recovery type site there using data lifecycle to kind of move that data off to the right. And I'll talk about that one more time at the end. So moving up, we get to this egress solution. That's kind of the box in the middle. And the egress solution is, OK, so how do people actually use this data? How do we actually make it available? Well, it turns out we deal with really kind of 4 classes of egress. On the far right-hand side of this slide here is the AWS compute. That's, in some sense, the easiest one. That's I'm going to spin something up. I'm going to hit the data. It's already sitting in S3. So we're going to kind of ignore that one for right now. But we're going to talk about these other pieces. And the basic, simplest egress solution is we just expose the S3 buckets out to the internet, let people pull data out of S3. We can get fancier, and we can put something like CloudFront in front of it and do distribution that way. We can get another notch, right? NASA has a lot of infrastructure that could be leveraged. We could do a direct connect and then do distribution through an on-prem pipe or kind of out of existing infrastructure. Or we can kind of go even fancier and get to this idea of request limiting with Lambda and API gateway and kind of doing signed URLs, and kind of that lets us manage kind of egress information. The key thing here is not so much these potential architectures, but it's that just with those different architectures, with the same data moving through that, the cost is 13x from the cheapest to the most expensive. It is a huge deal. Egress is a big thing that we have to deal with and we have to pay attention to. But it wasn't our only issue. We have another piece of this. So by virtue of being a federal agency, there is this thing called the Anti-Deficiency Act. And the Anti-Deficiency Act basically states that we can't have an unbounded cost. So you kind of line that up against something like elastic compute, and we can just turn the knob and it goes faster, or it goes more. We needed a way of managing our egress costs. All right, so for that, we moved to something we called a circuit breaker. All right, so the idea of the circuit breaker, that analogy kind of holds. When you're in a situation of either your toaster oven's going to burn your house down or you throw the switch and turn off that outlet, you throw the switch. That's kind of the model we took here. This is kind of the, you hope we never have to hit this, but we can put this in place. And so conceptually, it looks like this. Conceptually, we have a set of Lambda functions that watch things that we can metric, whether it's an S3 bucket, data moving out of an EC2 instance, pick your thing. We take a look at that, and we look at some of the metrics, and we aggregate those up. And for any given application that we deploy, we have kind of thresholds. This data, we should always be below this threshold, whether we're using traffic shaping or whatever we're doing to kind of keep it below that, but it should always be below that threshold. We count this stuff, we keep track of it. We can do warnings at various levels. We hit 60%, 70%, 80% of the targets. We can start lighting up red lights in various places. But if we get close enough or we hit that limit, we shut it down. We can shut it down by changing an S3 bucket policy. We can change a security group. We can change a firewall port, whatever we need to do to effectively stop that bleeding. It shouldn't happen. We should never hit it. But this was a piece we had to put in place to kind of do cost controls, to make sure we had a hard cost control on top of this. Okay? All right. So where does that put us? It puts us here. Cloud scale science data. So we get to here, this architecture. We can generate data at scale in AWS, put the output in an S3 bucket, make it available that way. We have ingest, archive, distribution, and processing that can all scale dynamically. So if we're doing just kind of forward processing, we can configure it at a certain rate. It goes. We need to do reprocessing. We can blow out horizontally. We can reprocess as fast or slowly as we want based on costs or needs or whatever the particular thing is. But we don't have to provision or procure for kind of worst case scenario anymore. Again, we can kind of do this dynamically and at scale. Almost more interestingly, though, is we get the entire petabyte scale archive available for use. So right now, we're in the 20s, right? 20 petabytes. Get up to the 300, 400 petabytes. People looking to do long time series analysis, people looking to do heterogeneous data analysis across multiple products or kind of data fusion, those types of things, we now enable that for the entire archive. No longer do we have to provision storage for somebody who wants to use this and pull this down to an on-prem thing, or are people prohibited from doing kind of longer term studies because they can't get to all of that data. We now have the entire archive available for use and kind of enabling that type of information. And lastly, we get to this data processing, transformation, and analysis services. So now, with the archive available, we can begin to spin up services on top of this, whether they're NASA funded, they're third party, they're commercial, whatever. People can bring services up, do the processing, do the transformation, do whatever they're looking to do with that, and then spin it all back down when they're done. So we get here. All right. So looking forward, what do we have to deal with? So these are the parts that we either haven't solved or we're currently working on. But I'm going to talk about the first two in a little more detail, just a couple things that we've poked at and are kind of interesting here. Efficient data service access and distribution. So how do we do this? Those data services, people who want to do data transformation, you want to take this and it's in an archival format, HDF file format, and you want to turn it into a cloud-optimized GeoTIFF, or you want to turn it into a regular GeoTIFF, or whatever you're looking to do, or just JPEGs to put into a PowerPoint presentation. How do you do that effectively? How do we let them do that? Mosaicing, subsetting, and reprojection. Large archive storage, again, we're into the hundreds of petabytes, so how do we do that cost effectively and manage that and let that continue to scale? Disaster recovery and preservation, third-party cloud-native data use, so someone who just wants to compute across the whole archive, how do we do that in a way that we can do metrics and authentication and kind of data control and provenance and things like that and allow that to happen? And then the last one is social, and so I'm not going to talk about that here, but how do we transition an existing community? How do you change that paradigm of people who are used to pulling down data and running it on their machine? How do you then kind of entice them to say, look, if you come up here, we can actually do this at a massive scale and with a lot more data? All right, diving into those first two bullets, though. Efficient data service access and distribution. So this slide earlier, we were talking about it. The right-hand side, computing near the data. The left-hand side is effectively distribution. That's kind of the circuit breaker pieces and things like that. But really, this middle one, this data distribution from services, how do we do that? So this is where I want to pull everything down as a GeoTIFF. I want to pull everything down as a TIFF, or I want JPEGs. And how do we deal with that kind of approach? And we were in a conversation with the S3 team, Mark Korver from the S3 team with AWS. And he said, almost in passing, he made this comment that people think of S3 as a storage service, but really it's a distribution mechanism. And that was actually a really huge kind of like, oh, wait a minute. And so we went back and we started talking about data services really as just transformations between buckets. And so the idea here is, as a user, I make a request to some service, whether it's running in EC2 or it's running, it's an API gateway sitting in front of Lambda or something like that. But you make a request to a data service, and rather than streaming that data back out, instead stage it to S3 and return a redirect back out to S3. Like, this is not mind-bending stuff. But what it did was it shifted a whole bunch of problems that we were going to have to deal with. We were going to have to update services to deal with permissions and authentication and metric, and anybody who was building a third-party service that were plugging into us, they had to deal with a whole set of problems. By changing that model and saying, you know what, don't distribute data out of your service, stick it on S3 and return a URL to that, well, now we can take advantage of all of the stuff we've put in place for our distribution capabilities, authentication and redirects and throttling and metricing and circuit breakers and all the different stuff we have to deal with. We can offload all of that to the same infrastructure. Again, like, putting this diagram up, it's like, yeah, put your stuff in S3 and then it handles it. But this was a big deal in terms of rethinking the way we deal with services and moving data out of AWS. So I wanted to pass that one on. All right, cost-effective large archive storage. So this was one that we started prototyping. This is the Alaska Satellite Facility, ASF, did this work and were nice enough to let me leverage their slides here. So when we talk about storage, we're talking about S3, S3IA, Glacier, and then potentially look at the disaster recovery on-prem. And we can use data lifecycle to kind of move data through that. But the question that somebody asked was really, could we look at past user behavior and do predictive analysis to figure out where to put this data to begin with and not even have to pass this kind of through that life cycle and move it all the way back to Glacier and avoid that if we can? So the hypothesis they threw out was, OK, data that's used more than 4 times in the last 30 days, let's put that in S3. Within 30 days, it goes to IA, infrequent access. And then if it's never used, just put it right in Glacier. And so we kind of mapped, well, see, here it is. All right, so we did that. We talked about that, and we said, OK, so could we predict this based on current usage? So we leveraged AWS's machine learning infrastructure. This is not, we didn't do kind of custom model development and fire up TensorFlow. Like we leveraged AWS's managed service for machine learning. And what we did was we put all the records for products ingested January 2017, pulled their download history, and set the training column just looking at the classifier, basically just looking at was it used more than 4 times in that month. So that puts together this massive spreadsheet of kind of everything we could kind of grab easily. And so looking at product ID, looking at size, acquisition start and end, spatial bounds, just kind of throwing all of the easy metadata stuff we could get together along with was this used or not. And then fed this through as a training set. And what we found was it came out kind of interesting. It was this slide doesn't show this is an earlier version. It's still being evolved. We have not deployed this. But we could get a reasonable guess. And what that really meant was now it really became this kind of conversation of how much does it cost us, either in time or dollars, to pull it out of Glacier if we're wrong, and then just balance those two and say, like, OK, it's OK to be 80% accurate. Or 75, or whatever level we kind of need before the economics shift that to say, what, it just makes sense to stick it in Glacier. It's OK if we're wrong because we can pull it back out if we need it, if somebody hits that data and we were just wrong on it. So this is how we're looking to kind of get past just basic, simple lifecycle stuff and getting to really knowing where to put that data to begin with. All right, so where does that leave us? Kind of in summary, we're seeing the same data explosion that is being felt across this industry. And it's going like this. It's not a linear growth. It's a curve. And it's fast. In addition to that, the cloud not only gives us a way to kind of deal with that data, but it gives us an opportunity to kind of change the paradigm. How do we build software? How do people consume the data that we're using? How do we monitor, metric it, scale it? All of those pieces. This is an opportunity that really it's almost generational. Like, this is a big deal that we get this chance now to kind of look at these and make this transition. Effectively exploiting cloud-hosted data is still an open issue. So there's still too many cases where we're going to fire up something like Jupyter Notebooks, or I'm going to fire up an EC2 instance and just copy a bunch of data out of S3 so that then I can run it. Or I'll use YAS3FS and kind of just mount an S3 bucket and process it. This isn't really a solved problem, and it's still something that we're trying to figure out how to kind of deal with. We do a lot of packaging up of legacy Fortran code that's been scientifically vetted. It's very valuable algorithms, but they have to get packaged into a Docker container and then run in some way that can process against this data that we now have sitting in S3, and kind of how do we manage that. Authentication and metrics is still an issue. Again, it's kind of the same problem. How do you not get in front of all of the scalable systems? If you take S3 and you put that there, and then you put an authentication system in front of it that can't scale, we've defeated the purpose of putting that stuff up there, and it makes it really difficult to use. So it's something that we have to deal with. And then lastly, as Kevin mentioned, most of this that I've mentioned is up on GitHub, either under GitHub/NASA, or if you do some Googling, it may be under a slightly different branch in GitHub, but it is there. And then as we continue, as more pieces are built, they'll end up there as well. That is all I have. That's it.
All right, I think we have a few minutes for questions. If anyone has a question. Yeah, go ahead. I don't know if there's mics floating around.
Just yell. We'll repeat it.
Yell.
What capacity of links have this large amount of data between NASA and the storage of the cloud, the connectivity, the transport?
So your question was, what's the connectivity between NASA ground systems and? So I think we have direct connect links. I don't know if they're 10 gig or
I'm not sure what the exact.
40 gig connections through either Internet 2 or, yeah, primarily to push it up. And then we use Amazon itself. That's the idea, to distribute it. Right, no problem.
Thank you. Other questions? Yeah.
Yeah, hi, question for Dan.
Yeah.
Of that architecture that you described, how much of it is serverless?
Depending on how you count the Elastic Container Service, just about all of it. If you count, the container service is kind of a managed service, so we have Docker containers, but we don't have to manage the host nodes. So that's kind of, if you squint a little, you can put that in the serverless category. But kind of all of the bookkeeping, the general forward processing is all serverless.
All right, great, thank you.
Yeah.
How are you doing your geo searches if you're putting everything in S3?
So the geo services, so that's the CMR's job, the Common Metadata Repository. And so what we do is we extract, so the source data comes in, we extract a set of metadata. The metadata has spatial bounds associated with it. We actually use Elasticsearch for that. Because of the types of spatial searches we have to do, the polar searches that Kevin had mentioned, we have kind of satellite swath passes and complex spatial filtering. We've actually had to write a custom plugin for Elastic that'll do the spatial searching against that. So we create a spatial index and then hit it that way. And that's also on GitHub.
So you're running your own servers?
We had to, yes. I can't tell you how much I would love for Joe to say we could just put a custom plugin into the managed Elastic service, but we can't. So we have to run our own Elastic cluster. Big one. It's not as big as you'd think. It's double-digit nodes, but small double-digit nodes. Is that fair? Yeah. But I mean, they're in AWS, but we do run them up there. Yeah. Not on containers. No.
Thank you. Any other questions? Yeah.
You have the NISAR data that you were talking about. Do you see any startups working on the data being generated by NISAR yet?
So NISAR doesn't launch until 2021, but there are some free data from Sentinel-1 from the European Union's Copernicus program, and those have certainly been used by startups. We have a mirroring agreement with ESA and EU, although you can also get those products from ESA itself. Okay.
Any other questions? Yeah.
You had a bullet in your slide about disaster recovery. How do you do that?
Now we're in the future.
Yeah.
Those are two different
questions. In the future, there's an effort going on right now in terms of basically preservation. So NASA has a preservation responsibility, a preservation archive to make sure that or obligation to make sure this data is safe. So right now, because we want to be able to do some processing and generation in the cloud, what's being prototyped is effectively hooking the Cumulus ingest piece so that as it's being ingested in a copy, it's being put in S3, we're also staging it for an exfil back to an on-prem location. Whether that's an on-prem, actually I shouldn't put it that way, we're staging an exfil somewhere, whether it's another cloud provider, another on-prem or whatever.
We have specific rules and regulations we need to follow in terms of Data Retention Act and those types of things. So we'll likely have multiple copies, both from kind of the ground recording stations all the way up through the archives. And we currently, have things at White Sands and other locations for kind of long-term storage of those level 0 products, higher level products, we keep for some period of time until a new version's made, and then we get rid of the old one and have offsite backups. We'll probably embrace something similar to that in the future, although we might use multiple cloud providers and an on-premise solution, right, as well. But you can't launch another satellite 30 years ago, so we need to be very careful on how we manage these products.
Other questions? Yep.
Excuse me, are you using any type of analytics services like Athena, EMR?
Nothing in what I showed today. There have been prototypes looking at things like Athena and repackaging some of this data into Parquet. But there's kind of a conceptual split we have. So we have kind of the ingest archive preservation responsibility, and that's really get that data somewhere safe and with multiple copies, and that it kind of there. And then there's kind of a use component of, okay, now what do we do with it? And so converting it into, whether you want to load it into Redshift or Redshift Spectrum, or like there's lots of format transformations that kind of have to happen to enable a lot of those analytic services. And so at that point, so yes, there's been prototypes in there, but nothing in what I showed today. What I showed today basically stops at the data is safe and available, and then people could build solutions like that on top.
And maybe we should give you a little context in terms of where we are with this, right? So for about 18 months, we needed to prove that we could afford it, that we could operate these types of NASA archives in a commercial cloud environment, because there are a whole set of rules for procurements and security and other things that don't apply to normal people, right? And we had to get across all of those types of things and through those. And we were able to basically prove that over the past couple, 18 months or whatever. We're really transitioning into the I can't say the word, but operationalizing these capabilities for the future, right? So I think over the next 2 or so years, you'll see kind of the traction that we have moving these products into the cloud accelerate pretty significantly. And part of that is devoting some of our competitive research funding, right? That people can apply for and get grants to build some of those analytic services, right? So like I was mentioning earlier, we do have this access program out right now, and if you partner with Amazon or somebody, you can certainly take advantage of those types of things to help our users use the products a lot better. But we are going to be investing quite significantly in kind of making it a lot easier for a lot of people to use these products.
All right. Thank you, everyone. If you have any questions, just find us later. I think we're out of time.
Thank you.
Thank you.